Hi everybody. So, this would be our first lecture for the course on GPU architectures and programming. So, from our introductory video, we have provided a brief outline of the different topics that we are going to cover in this course, and just going through some of the related slides of that video once again for our purpose. So, this is just again going back into the history, as we explained that in earlier personal computers, we had this notion of a graphics pipeline which was functioning in the form of a video graphics array, which eventually got replaced by a more programmable version, that is the graphics processing unit or the GPU. And eventually people found that since this is a programmable parallel processor, it can be used for accelerating lot of general purpose workloads, which is basically giving rise to the term GPGPU or general purpose graphics processing unit. And we also provided this snapshot of how a standard CPU connects with the VGA and other related peripherals, vis-a-vis how really the architecture of a GPU looks like, with a lot of processing cores inside it, which are the SPs or the scalar processors. This is just to give an idea that I can view a CPU as a maybe a multi-core platform containing a small number of compute cores, whereas a GPU essentially contains thousands of compute cores, though simplistic in terms of functionality, but lots of them. With this basic background, we have already introduced the course organization, out of which now we will get into the review of the basic computer organization and architecture, which is the topic 1. So, let us get started with that. So, we will start with a brief overview of what we have historically known as the classic 5-stage RISC pipeline. So, what is RISC, by the way? Now, RISC is more of a computing philosophy which evolved as a separate philosophy vis-a-vis the then practiced philosophy of CISC, which essentially meant complex instruction set computing, while RISC meant reduced instruction set computing. So, what really are these things? To get into that, let us just browse upon what does a processor really do. A processor is a digital system which is executing a few specific operations in the loop continuously. A processor crunches instructions which we have been knowing from our basic background as assembly instructions, which are getting compiled by which are getting assembled by a software called assembler to machine instructions. A processor processes such machine instructions through a standard loop of fetching the instruction, decoding the meaning of the instruction, and finally executing the instruction, and then again jumping to the next instruction. How a processor really goes about this business is where the computing philosophies differ. So, fundamentally this style of whether to follow RISC style of computing or CISC style of computing is based on the basic notion of instruction set of a processor, that is, what are the different types of machine level instructions a processor is going to support. Are those instructions going to be very simplistic activities, or are the instructions individually powerful enough to do lot of things by just one specific instruction itself? So, this is where these philosophies differ. That is why RISC is reduced instruction set computing and CISC means complex instruction set computing. So, coming to the CISC approach, the philosophy of CISC is essentially that a processor should try and complete a processing task using as few instructions as possible. That means, when a program is compiled to generate code for a CISC processor, the number of one of the basic objectives of the code generation process would be to represent the program in terms of assembly instructions and thereafter in terms of machine instructions using as few instructions as possible. That means, each of the instructions are going to do a hell lot of work. For example, let us take a CISC instruction as we have given here, that we have a multiplication operation mul with 3 operands, address 1, address 2 and address 3. Essentially, we are meaning that while executing this instruction, the processor shall fetch data from the memory address 2 and memory address 3, multiply them and store the result back to memory address 1. Now, of course, as we can see that this is quite a lot of job. It is going to load data from the main memory, it is going to multiply those data points and it is going to store the result back to the main memory, all done by executing a single instruction. Now, in terms of hardware design, that means we are thinking of a hardware which is complex enough to do all those things by executing a single instruction. The RISC philosophy is diametrically opposite to this. So, in an equivalent RISC world, we do not have this kind of a multiply instruction. In fact, that would get replaced by a sequence of these instructions. So, there will be a load type instruction using a load command. One should be able to load the data from memory address 2 to some register R2. This will be followed by another load command through which one would be able to load the data from address 3 to the register R3, and then we have a multiply instruction. So, as we can see, this multiply instruction takes as arguments contents of registers R2 and R3, multiplies them and stores the result in the register R1. Now, this will be succeeded by the store instruction, which will store the result from R1 back to the memory address 1. So, essentially this kind of summarizes the RISC philosophy, that all kinds of operations, specifically arithmetic logic operations, they have to happen over data values that are present in the register. The result of such operations shall also be stored in registers. There is no operation that is going to happen on values stored in the memory. So, the only instructions which are going to write or read data from memory are the load and store instructions. So, this is one way to represent the difference between a complex instruction and the equivalent case of a sequence of simple instructions. So, when we say that it is a RISC processor, it is a processor where the instruction set comprises only these kind of very simple instructions. When we say it is a CISC processor, the instruction set is arbitrarily complex. There are instructions which are very powerful by themselves, doing a lot of stuff. Overall, to summarize the difference, the CISC features, the features of a CISC kind of system. The instruction set architecture of a CISC processor is older. The philosophy is quite old. So, CISC processors came much earlier. RISC was an idea which emerged in the 80s. Earlier to that, it was mostly CISC. Instructions used to be multi-cycle. That means the processor is driven by a master clock, and each instruction's execution shall consume multiple clock cycles. Of course, because each instruction is going to do a lot of work. So, it is a hardware intensive design, in the sense it may be the case that for some powerful instructions you need some specific hardware unit built into the system. Vis-a-vis the RISC feature is that all the instructions are single cycle. Every instruction will do something very simple, but at the same time, since it is going to do something very simple, it will consume a single clock cycle and get the job done, which would mean for the same functionality, the number of instructions in CISC is less, the number of instructions in RISC are more, but each of them execute faster. So, overall, the timing for the final task may not differ much. It is how about the system goes about achieving the job. That is why we say CISC is a hardware intensive design, because there may be more specialized hardwares for specific kind of instructions, and RISC is more of a software intensive design, because I am breaking every task into small atomic instructions, which would mean for every task I will generate lot of instructions in software terms. Now, since in CISC I have much less number of instructions to execute, the RAM usage is much more efficient, whereas for the equivalent functionality, since I have a big code to execute, the RAM usage is much heavier. And also, since all RISC operations are to be carried over operands from the register file, specifically the arithmetic and logical operations, I need the support of a much larger register file when compared with CISC. Other important thing is, in CISC the instructions are complex, they are multi-cycle, which also means the number of cycles required for executing each of the instructions may vary. Whereas, as we have discussed in RISC, all the instructions are single cycle. Now, another very important thing is, since there is no regularity in terms of the intensiveness of CISC instructions, some instructions may be very complex, take multiple operands, take multiple cycles to execute, and due to its inherent complexity in terms of specification as well as number of operands, the instructions encoding length may be very big, whereas for some other instructions, some other CISC instruction, the instructions encoding length may be small. Overall, the point is the CISC instructions may vary in length, whereas for CISC, for RISC, the instructions, all of them are very regular, they are going to be of a same fixed length, because they are quite generic, they are all single cycle, their intensiveness in terms of hardware usage will be kind of similar. So, they will all be of similar, exactly same opcode length. Another very important CISC feature is compound addressing modes. There will be lot of different support for multiple possible different addressing modes in a CISC ISA or instruction set architecture, whereas in RISC there will be much less number of addressing modes that would be supported. To get into more details about these features, is best that one should consult any well-known undergraduate book on basic computer architecture, but these are the important points which we wanted to summarize as the difference between these two very well-known computing styles and their adoption in basic processor design. In modern days, possibly apart from x86 architecture, all other processors, more specifically in the embedded world, the processors used in mobile platforms, they are mostly following the RISC computing philosophy. In the other terms, that means in the x86 world, Intel has still been able to hold on to the CISC philosophy, but internally there is also a question of translation of CISC instructions, but those are like advanced topics which we may touch upon later on. Just an example of a CPU data path. So, what is a data path? This is basically a drawing which is trying to summarize how the different functional units inside the processor are going to be connected. As we can see, there is a block which represents the instructions and their storage in memory. There is a block which represents data and their storage in memory. Now, of course, in a general processor, instructions and data will be resident in the same memory for a von Neumann architecture. This block highlights the register file which will be containing all the CPU registers, and this is a block which is more representative of the ALU. Now, this is kind of a very simplistic CPU data path which is trying to convey the basic operations that a CPU is going to execute. Like we have said, the CPU's data path is going to execute three basic operations for now: fetching the instruction, decoding the instruction, and executing it. Now, these are the functional operations, which means it will take one instruction, understand the semantic meaning of the instruction, and do exactly what the instruction wants to do in terms of functionality. But thereby there is also the question of reading and writing operands from the memory as well as updating values in registers. Now, this will also give rise to some more functions which we will see soon. Now, coming back to the question of data path. So, the data path essentially represents the flow of data among different functional units as captured in this picture, like how exactly the data flows from each of the functional units, what are their dependencies, and the more important thing is how is the flow of data controlled. Now, you can see that there are certain signal lines here which are marked in red. Now, these are the lines which are expecting some digital commands based on which they decide how this digital system would operate. Fundamentally speaking, the data flowing in from a hardware unit should be used for what kind of functionality inside the hardware unit and should be routed as an output to which hardware unit. This is what is dictated by these signals marked in red, and they are known as the control signals. The control signals get generated through a separate logic called the control logic. Now, as we have discussed earlier, that in RISC the philosophy is that every instruction executes in a single cycle. Now, why is that a good thing? Now, let us note the important thing that even for RISC style instructions, each instruction may have different timing delay when the functionality is implemented in terms of hardware. That is why we can say that instructions execute with variable delays in a CPU data path. Now, the question is, when I have implemented such a data path in hardware, this is a digital data path, it needs to be clocked by a suitable clock signal, and I have to choose a suitable frequency or period of the clock. Now, as is standard in any digital design, the clock period is chosen by looking at the critical path of the circuit, that is what is the situation in which the data path or this specific digital circuit will incur the maximum delay. Now, as we have said that even for instructions which are all lightweight and atomic as in RISC, their executions may create different possible delays in a data path, right. So, then does it mean that the clock signal's frequency should be different for different execution of instructions? No, that is definitely not possible. That means we have to find out execution of which instruction takes the most amount of time and choose the clock period to be equal to or greater than the latency of that slowest instruction, right. Now, even if we do that, we still have a problem, right, because then we may have a system where I have multiple possible instructions to execute. Some of them are very slow in terms of hardware latency, some of their executions is very fast in terms of hardware latency, but since I have chosen the clock period so that it can execute the slowest instruction, even for the faster instructions and their execution, I suffer the delay of the slowest instruction. So, that leads to a very conservative design. So, how do I get out of this problem and increase a processor's or a CPU data path's throughput? The way to go about it would be that look at the instructions execution path, what are the basic functionalities that each instruction is supposedly going to do, and break that into a set of basic operations or basic steps. Now, why do we do that? Because if I can break this execution of an instruction into certain basic steps with respect to the flow of data and control and processing in this data path, then I can now clock each of these basic steps by a fast clock. How does it help? The basic steps are simple, so they can be clocked by a fast clock. For some instructions I may need a sequence of all the basic steps, for some instructions I may not need them, which would mean now I would really have this system driven by a fast clock with some instructions completing fast and some instructions completing slow based on what is the requirement of the instruction in terms of these basic steps. Now, if we get into this issue of identifying the basic steps required for executing an instruction, earlier we have been telling like an instruction needs to be brought from the memory, it needs to be the meaning of the instruction needs to be brought out by the decoding the instruction and finally executing the instruction. And at the same time we also said okay, this is fine, but there is also this issue of bringing data from the memory, updating the data in the register file and all that, right. So, bringing all these issues together, we can say that the execution of any instruction in a RISC kind of system can be broken down into these 5 basic states. The first stage would be what we call the instruction fetch stage, where the value of where actually we check the content in the memory for a location that is loaded into the program counter marked here by this PC, right, and load the content into this specific register which is called IR, the instruction register, right. So, I hope everybody would be familiar with these notions of program counter is basically a specific register in your CPU which loads a specific memory address from which you are supposed to fetch the instructions and execute them. So, this is noted down here in terms of these standard mnemonics that you can find, that the content of the memory location that is pointed to by the program counter is getting loaded into the instruction register, followed by the program counter getting incremented by 4. Why? Essentially we are thinking that memory is byte addressable and the memory word lengths are 32 bits. Assuming that we should get the next program counter value by incrementing the current program counter value by 4, right. Now, what is the next stage? So, the next stage would be this decode stage. That means an instruction has been fetched. An instruction is nothing but a sequence of ones and zeros. In our assumption here it is a 32-bit instruction, and this sequence of ones and zeros need to be understood by the CPU. So, there is this decode stage where based on the instructions encoding and its operands, the CPU should understand, more specifically the data path should understand what does its instruction want to do. It is a load instruction, it is a store instruction, it is an add instruction, what does it really want to do. Based on this understanding, it should activate suitable functional units in the next stage, that is the execute stage, and it should perform the required operation depending on whether it is an arithmetic or logical operation, whether it is the computation of a memory address for a branch or whether it is the computation for a branch condition itself. So, these are the computational requirements which, if there is any, will be computed in the execute stage. Now, this execute stage has to be followed by another stage called the memory stage. Now, what is this for? In case the instruction is a load store type instruction, it needs to fetch data from a memory location and that data has to be loaded into the register file, right. So, this fetching of data from the memory will be performed in this memory stage. So, basically this is the stage which is going to handle all read writes from and to the memory. Now, we have the last stage in the pipeline which is called the write back stage. So, any kind of update that is going to happen on the register file has to happen here. For example, if I take the example of a load instruction, so suppose I am loading the value from some memory location X to some register R1, the access of memory location X and fetching the data from that location to some specific register called memory data register should happen in the mem stage, and then writing this data from the memory data register to the specific register R1 in the register file, this update of the register file shall happen in the write back stage. So, these are the 5 stages which more or less characterize the execution sequence to be followed in a basic RISC processor. That is why we call it the classic 5-stage RISC pipeline. Now, of course, in a real processor there are much more complex functionalities present in a basic RISC processor. There may be many more pipeline stages present there, but for our purpose we stick to this discussion of a pipeline with our understanding of this basic 5 stages of execution. So, overall, when this pipeline operates, every instruction has to go through the sequence of 5 pipeline stages from instruction fetch, instruction decode, execute, memory and write back. It depends whether some of the instructions will really need something significant to be done in that stage or not, but all these stages will be active. Since the performance, the functionality of each of these stages is very basic, there can be a faster clocking all these stages, so that depending on the instructions execution, I mean we will have a fast execution of all the instructions, whether or not it really needs executing in that stage or not. Now, once we pipeline the operations in this kind of a processor, I can always have these basic stages always processing some instruction, which means suppose I have instruction 1 entering the pipeline, that is, it has been fetched and it has been decoded. So, when the instruction 1 is going through the decode stage, I can have instruction 2 being fetched, and when instruction 1 is getting executed, instruction 2 can get decoded and instruction 3 can be fetched. So, that would mean if I look at the pipeline from its end point, I always see one instruction getting completed, right. That means in that way I can say that overall the throughput of this pipeline is one instruction getting executed in each clock cycle, getting finished with respect to execution in each of the clock cycles. So, this is where the optimization really helps. To summarize from the earlier points, had we been sticking with a single cycle implementation of our CPU data path, the single cycle implementation would have required different amount of time for executing each of the instructions depending on the instruction's functionality. In that case, the choice of clock would be based on what is the slowest instruction, and then what would happen? The lighter instructions will suffer the same latency as the slowest instructions. In order to alleviate that issue, we broke the execution of instructions into this kind of basic stages. Since each of the basic stages are very simple, we are able to clock the pipeline with a very fast clock. Since that is the case, and I can keep each of these stages always active, I can keep on filling instructions at the front of the pipeline, and I can see instructions getting completed at the end of the pipeline, one in every clock cycle. So, overall, using this idea of pipelining, starting from multi-cycle execution of instructions, we are able to see every instruction, I mean the pipeline is able to complete one instruction per clock cycle. So, in that way I can say that every instruction requires one clock cycle, but that is not really the case, right. Every instruction is requiring 5 clock cycles with respect to the basic stages, but since the pipeline is always active, it is interleaving the execution of instructions, I can say that finally from a user's point of view, every RISC instruction, I mean when it executes through the pipeline, I have one instruction completing in one clock cycle. Now, this would really be the case in an ideal scenario. So, what is a non-ideal scenario? Non-ideal scenario means that while executing an instruction in a stage of the pipeline, it may so happen that immediately the instruction is not able to execute in the next clock cycle in the next stage of the pipeline. These are the issues known as pipeline hazards, which we will be covering. Thank you.